Welcome to the fourth in our Masters of Reliability webinar. Today's topic is risk-based asset planning for cables. My name is Chrissy, and I'll be your moderator for today's session. Rich Brinton, Vice President of Business Development at Novinium, is here with me as well.
Welcome, everyone.
Joining us today is our expert guest speaker, Robert Otel, Director of Asset Management and Analytics at Metzco Energy Solutions. Mr. Otel holds a degree in electrical engineering from Ryerson University, is a registered professional engineer in Ontario, and a member of IEEE. As Director of Asset Management and Analytics at Metzco Energy Solutions, Robert consults with utilities to optimize their asset management processes and systems and improve justification of plans and components for the regulatory environment. Prior to joining Metzco, Robert worked with Toronto Hydroelectric System Limited, improving the utilities distribution system, and Horizon Utilities, implementing an asset management plan and condition assessment system. Robert and Rich will be answering your questions at the end of the presentation. If you'd like to submit a question, please use the chat box on your screen. There's also a brief survey at the end of the webinar, and a recording will be available on novinium.com. Robert, welcome, and I now turn the presentation over to you.
Thanks, Christine. And thank you, everybody, for joining the webinar today. I'll be talking about risk-based asset planning for cables. I wanted to thank Novinium for giving us an opportunity to participate in this webinar for today. Just wanted to give a quick rundown of the agenda. So we'll be talking about a risk-based approach for cable investment planning, and that involves discussing the building blocks of how we perform a risk-based analysis, beginning with the probability of failure. We look at the cable's condition assessment data, deriving failure curves, and then looking at the impact of cable failure, and that's looking at consequence costs, and then putting that information into a risk-cost calculation and performing an economic analysis to perform and produce business cases to help us justify when do we want to intervene on the cables and what type of intervention should we perform. Should we replace or should we rejuvenate the cables based upon a life cycle costing and cost of ownership analysis. Just to give a bit of background on Metzco, so we're an engineering consulting firm, and we specialize in areas such as asset management, engineering design and planning, and providing support to utilities as part of their regulatory applications and justification. With respect to asset management, we've been creating some of the very first technical documents around asset condition assessment and health index solutions. Some of the earliest papers were authored by our teams back in 2002 and 2003. We serve clients all across North America and internationally, with 50 clients in the electric power industry, from generation, transmission, all the way to distribution. We've evaluated over 70 different types of asset classes. And in that time, we've seen health index truly mature in the industry. It's accepted by regional regulators, and we've successfully integrated this approach as part of a risk-based asset management planning solution. Just to give you a holistic view of what we'll be talking about today, it's really beginning by looking at the health or measuring the condition of the cable assets through the use of a health index, translating that information into a failure probability curve, and then looking at the consequence costs such that we are able to determine and quantify the risks of cable failure. We can perform an economic analysis using what we call life cycle costing and total cost of ownership. And the total cost of ownership, or really the reduction of total cost of ownership, is what we are using to measure the benefits of cable replacement or rejuvenation. And that information is ultimately used as part of long-term and short-term planning outputs that the utilities can use to justify their investments to regional regulators. In terms of the cable planning approach, this really begins by looking at the utilities' data, relating to cables. That includes condition assessment information that can be used to determine the failure probability of the cable. And it also involves the quantification of the cable's impact if it fails. And these two components can be used to measure the risk of cable failure. That can be used ultimately as part of a life cycle costing and total cost of ownership analysis. So I want to talk about the individual building blocks that we're using as part of this risk-based assessment, beginning with the cable's condition assessment or health index. How do we develop a health index for cables? Well, we start by building an architecture with the help of subject matter experts at a utility who have knowledge of the specific types of cables or subtypes of cables that are introducing problems within a given distribution or transmission system. And then we'll also look at all of the different types of data that would be available on underground cables. We'll look at the testing information, we'll look at maintenance and inspection information, and from all of this we're able to develop an architecture that can be used to quantify individual health index results for each individual cable segment. And that will be done using the individual cable's asset age, the inspection data and local data that we have on that cable, as well as degradation factors which are individually weighted as they relate to the overall probability of failure of the cable asset. Some of the issues that we've seen with polymeric cables, especially those installed between the 1970s and to the 80s, include water tree phenomena, imperfections with respect to the jacket and semicon, and this can lead to issues such as overheating, partial discharge, and leakage around the splice, joint, and terminations, tracking and erosion. With oil-filled cables, we also see dryness phenomena. So how do we combat all of this? We can develop a health index for cables, and this shows an example of how a health index can be implemented for polymeric XLPE cables. Now, the health index is going to contain individual degradation factors. Degradation factors result in irreversible damage to the cables, resulting in the overall probability of failure of the cable asset. And so in this example, we have 3 degradation factors, including the service age, historical failures or cable failure analysis, and then the cable's historical utilization or loading history. And each degradation factor is going to be individually weighted as it relates to the probability of failure of the cable. And then depending on the utility's processes, either a letter grade or a numerical score will be assigned to each degradation factor. And each degradation factor will carry a maximum score that it can achieve. And so in this example, the highest score that could be assigned to this asset would be 100, meaning that it would be in very good condition. And the lowest score, which would be a 0, would mean that the asset is in very poor condition. Now, each of these degradation factors, they're going to have individual grade levels, and there's going to be definitions for each grade level. So in this example, we see that if you have, based on the service age degradation factors, if we have a grade of A assigned to a given cable, it also carries the youngest age. It's younger than 15 years of age. If we have a grade of E, it's going to be older than 45 years of age. And we can translate those letter scores into numerical scores. So the grade of E, the highest, translates into a score of 4. The lowest E translates into a score of 0. And we see similar grades and definitions for the other remaining degradation factors, for cable failure analysis and for loading history. And so if I take you through an example, we could have a cable that has a score of 3 and it has a weight of 10 for service age. So that would translate into a service age score of 30. In terms of the failure analysis, so maybe it has experienced a lot of failures, so it ends up with a score of E or 0, and failure analysis is given a weight of 10. So it would be assigned an overall score of 0. And then the loading history, perhaps it's been assigned based on its utilization, a score of C or 2, and loading history carries a weight of 10, so it would get an overall score of 20. And so then based on these individual scores, 0, 30, and 20, we subdivide this into the maximum score that could be achieved for that cable segment, and we translate that into a percentage. And so in this example, we end up with an overall health index of 50% or fair. And as I mentioned before, the health index numerically can vary from the best score of 100, which is very good to fair to poor, all the way down to very poor, and very poor would be anything between 0 to 30%. Now, based upon these results, this can provide an immediate view to utilities on what assets they should replace and what backlogs would they face depending on the different health grades. So how many assets do utilities have that are, for instance, in very poor and poor condition, which would need to be managed in the near future? And so in this example, we're looking at the replacement value of the assets as they're categorized by asset class and as they're categorized based on the different health grade definitions. And so this gives an indication that, okay, 8% of the distribution plant or replacement value is in poor and very poor condition, and that translates into about $45.7 million of near-term investments that they're going to have to make. And the replacement value, that's really based upon the total cost of replacing or rehabilitating that equipment based upon material, labor cost. Now, the last step is we want to be able to translate that health index score into a condition-based failure probability result. And in this example, based on the green curve, we see that this particular cable is failing at an accelerated pace based upon its health index result. So I want to talk a bit more about the failure curve calculation, how that allows us to predict the failure of the asset based upon either the age or the condition. How are these failure curves developed? It really starts by looking at the asset life data for each of the asset classes, including underground cables. So we're going to look at when the cables were first installed and when were they ultimately removed from service. We want to make sure that the data has been properly filtered such that we are only including those cables that actually failed or had been proactively replaced due to imminent failure. And if that information is acceptable, we can include all of that as part of what we call a probability density function, or PDF, and that will eventually get translated into a hazard rate function, or HDF. And here's an example of what that hazard rate function looks like. The hazard rate function is really the final failure probability curve that relates the asset's age to the failure probability. This is an example for cables. And in the case of cables, not only are we looking at the age, but we also look at the length, because the failure probability calculation is computed on a per meter basis. In this particular example, we see that for XLPE cables, when the cables had historical events or splices, so splice history, we found that the cables were 3 times more likely to fail as opposed to cables that had no splices at all. So once we've determined the probability of failure, the next step is to figure out what's happened when the failure occurs. What are the consequences or the impacts of failure? And so as an example, if I look at this chart at the top here, I see a given asset. It has a failure probability of 5%. We can subdivide that 5% into different failure modes. And here we see a specific failure mode table for cables. These are cables in cable chambers. We have XLPE and PILC cables in cable chambers. And each one has a specific failure mode assigned to it. We have relative probabilities for each one. So we're saying that a cable 95% out of that 5%, it could be just a normal failure, or 4.5% out of that 5%. It could be an instance where the duct has collapsed or there's no spare ducts available, or maybe 0.5% out of that 5%, it could go completely catastrophic. And for each one, we want to try to figure out, well, what are the root causes that could result in those failure modes? And then we also want to figure out, okay, what were the outage durations? What was the impact to customers? And then were there other impacts in terms of collateral damage? Were there environmental impacts? What is the overall scope of that outage? We want to consider all of those things when we are measuring the impact of failure. In terms of some of the data that we would use when we're trying to monetize the impact of failure, we want to try to take a look at outage information, historical injuries that have taken place, take a look at some root cause analyses of damaged equipment, property damage, data on oil spills and leakage, take a look at any cases of death, revenue loss, and claims that may have been filed against the utility. And then all of these can be used to establish different categories of consequence for a utility. And so the most frequent categories we've seen used include financial. These are the direct costs of intervening on the asset, so either replacing or rejuvenating a cable, for instance. There's the customer impact, and that's in terms of the reliability impact that the customer sees when the outage occurs. There's environmental impacts. Those could be things as they relate to oil leaks, PCB leaks, and then collateral damage impacts. That can relate to anything related to safety, injury, damages to adjacent property when a catastrophic failure is taking place. Now, the customer impact is obviously one of the most critical elements. And how do we come up with that customer impact? Well, we use customer interruption costs, and those are derived by really understanding what's happening when an outage takes place. We can subdivide an outage into an event and a duration stage. So when the event takes place, it means that all activities involving electricity are immediately terminated. I would no longer be able to deliver this webinar to you today. There's an immediate impact, an immediate shock to the customer that can be monetized, and we would treat that proportionally to the customer load measured in kVA, or dollars per kVA. Then you have the duration stage where the customer has readjusted their activities to account for the loss of electricity, but their inconvenience is still proportional to the duration of the outage. So we monetize that in terms of dollars per customer load hour, or dollars per kVA hour. Now, these numbers are typically generated by performing a series of surveys and advanced studies with customers in different regions across the world. We see some studies that have been done in North America and some studies that have been performed internationally to arrive at different event and duration costs. And we also see that these costs can vary substantially depending on the class of customer, from residential to small commercial and industrial to large commercial and industrial. We can see some substantive differences in these event and duration cost parameters. Now, it's important to note that residential customers, typically how their value of reliability is monetized is using a willingness to pay model, really asking customers how much would they be willing to pay to avoid an outage, compared to the data from small and large C&I customers, in which there will typically be direct revenue impacts and data available from those customer types, and that's really the direct tangible losses that those customers are experiencing. I should say that for residential customers, we are seeing more of that data, direct tangible losses, coming into perspective for that customer class as well, as more customers begin to do more operating businesses from home or working from home. So there are more revenue impacts that are becoming more relevant. But for now, if you just look at willingness to pay, what we see is that while we look at number of customers, yes, the willingness to pay compared to small and large C&I, it clearly dominates. But then in terms of how we convert all of that into a cost, recall that in our formulas we're using the consumption. And we see here that the consumption of residential customers is typically has to be weighted against the consumption of large and small C&I. And when we actually convert all of this into dollars, we see that the final willingness to pay value is actually a very small amount when measured across an entire utility system when compared to the total net dollar amounts for small and large CNI, which represents, again, the actual losses that are being experienced. And so what this shows is that really when you're looking at customer interruption costs across an entire system, it's really the actual loss data that's really dominating the equation compared to the minor willingness to pay costs. Of course, we have to look at other impact categories, including collateral damages, which would be a combination of things like safety-related incidents, the value of a life, claims filed against the utility. These are just some examples that have been performed for utilities in Canada. And then in terms of how the data is acquired in order to measure the impact of failure for each asset, what we will typically want to do is understand how are these assets all connected and configured within a distribution or a system. So for instance, if I look at this cable at the very bottom that's connected to this transformer, if this cable fails, it means that the utility has to basically replace this cable first before this customer can be restored, whereas meaning that it's a radial configuration, whereas you could have cases where a cable is connected and configured in such a way that customers could be restored from the other side because switching is available. And so all of those considerations, all those factors have to be taken into consideration. Now, once we've established the probability and the impact of failure, now we can establish the risk, and then more critically, we can figure out, well, when do we want to intervene on the asset, and most importantly, what type of intervention do we need to apply? Utilities are always facing essentially more and more challenges at a regulatory level. Regulators want to ensure that the utilities have considered every possible intervention option. And for cables, most importantly, it's critical that both replacement and rejuvenation are considered as part of an analysis. So when looking at, for instance, the total risk that can be measured within the system, once we've figured out the probability and the impact, we can measure what's the total system risk. And in this example, we see just over 70 million in risk across an entire system, and we see that the customer portion of that risk is clearly dominating that, that value, which is to be expected as reliability remains a critical element within any electrical system. And so once we've determined the probability and the impact, we can develop a risk cost, which is going to be increasing over time, this annualized risk cost curve in orange. But we're going to compare that against the annualized capital cost, the cost of installing that new asset. And so when we perform an economic analysis, the sum total of our annualized capital, annualized risk, is really giving us a life cycle cost or the total operating cost of the asset. Now, optimally, we want to replace that, we want to intervene on that asset at its minimum operating cost. But we have to consider that the existing asset to be intervened upon, the new asset to be installed, there's going to be different risks. For instance, you could have a direct buried cable as your existing asset, which may be replaced by a new asset in concrete cased conduit. So we have to consider that existing asset's risk cost curve. We have to cross-reference that minimum operating cost of the new asset to the existing asset. And what's that telling us is that it's at some point in time it's going to be more costlier to keep that existing asset in place when we compare it to the minimum operating cost of the new asset. And that's when we should intervene on the existing asset. We refer to this as the optimal intervention timing result. We can also call this the economic end-of-life criteria of the asset. Now again, when considering underground cables, we have to consider the different intervention options that can be considered. Cable replacement can be very expensive, especially when replacing direct buried cable with new standardized cable and conduit or cable and concrete encased conduit. And that's where cable rejuvenation can be considered as an alternative intervention, which allows for the extension of cables using a low-cost cable injection procedure. And so in this example, we're considering the alternative cable rejuvenation procedure by taking into account what are the rejuvenation benefits. In other words, once the cable injection is performed, we are extending the life of that cable by a certain number of years. And so in essence, let's say we execute that cable injection at this orange point or the existing cable age, we are offsetting or adjusting that risk cost. And so now we're following this blue curve here. And what we want to do essentially is calculate what is the difference of that adjusted risk, or the NPV of this shaded area here. That is really the benefit of performing cable rejuvenation as opposed to replacing the cable outright. And basically this net present value calculation, it's going to tell us whether we have sufficient benefit to performing cable rejuvenation versus cable replacement. And so when we perform that NPV, we end up with this parabolic function, this green curve here essentially. When we get to the top of that green curve, and we cross-reference it to the assets risk cost, that's when we can pinpoint the exact time when we want to rejuvenate the cable. Of course, we want the cable's current age to be within the parabola, and we want to make sure that the cable's optimal rejuvenation year comes before the replacement time. And in this example, it's telling us that it is more economical for us to rejuvenate the cable at 29 years as opposed to replacing the cable outright. Now, when utilities follow this framework and they replace their infrastructure at their intervene on their infrastructure at their economic end of life, in essence, they are reducing the total costs of ownership. And it's this reduction in total cost of ownership that we want to take a look at when trying to capture the benefits of doing the work. In essence, the difference in total cost of ownership, that net difference becomes the net present value or the benefit of doing the work. And again, we're taking into consideration all of the different concepts we talked about before, the financial, the customer reliability, collateral damage, and environmental categories. Now, we always have to include customer and societal risks as part of this analysis. The reason being, if we compare just the physical costs of ownership to the utility, which would be the asset-related costs, in this example, the vaults, the switches, transformers, poles, and cables, you can clearly see that that doesn't relate directly to the total customer societal costs. We see we have financial costs as they relate to the rate base, but then there's costs as they relate to interruptions in the system, environmental impacts, and safety costs. And so all of those things have to be considered within this calculation, and that's the only way we can come up with essentially asset management decisions that are truly taking into account the total customer value. So once we have been able to apply this approach to an entire population of underground cables, determining their economic end-of-life criteria, we can come up with a long-term investment profile like this, which is going to tell us which cables we are going to replace, which cables we are going to rejuvenate, and at what time we should perform those interventions. We see here at year 0 we have a backlog of assets that must be intervened. And in essence, when the utility has intervened on all of those assets and mitigated that backlog in that first year, we say that the utility has achieved an economic steady state by minimizing the operating costs across their entire system or for a given asset class. And as I mentioned before, this cost of ownership analysis can extend into other ways. We can take a look at different investment alternatives for a population of underground cable infrastructure. For instance, we can choose to continue to run cables to failure, or we can choose to defer investments and just install a series of fuses and switches. So we're improving operating flexibility, we're reducing further impacts of failure, or we can choose to perform full cable intervention at once. We can rejuvenate and replace a series of cables, all at once. And each of these strategies can be compared against each other by looking at what that net reduction in total cost of ownership will be. And so here's an example where we're considering the three options. In the status quo option, we see that when we're looking at run to failure, because really there's really no change in the total cost of ownership, your net present value is going to be zero essentially. If we choose to replace or rehabilitate the assets as per their optimal intervention time, we see some benefit. But it's only until we get into options 2 and 3 that we start seeing a substantial increase in benefits. Option 2 means that we're going to defer investments and we're going to install switches and fuses right away, and we see a substantial increase in net present value, meaning that we've reduced the total costs of ownership quite substantially. And in the third case, we're doing a full cable intervention. And in option 3, we consider two cases, one where everything is intervened, so the cables are either rejuvenated or replaced all at once, or we considered another scenario where we install the new underground switches and fuses immediately, and then we perform a full cable intervention 10 years from now. And we get the highest net present value of $46.3 million. And this is considering the cable's asset age and condition or the probability of failure. It's considering their individual configuration data for the impact of failure. And it's really telling us that it's better for us to perform targeted reconfiguration of the cable infrastructure immediately through the installation of the switches and fuses, followed by a deferred replacement and rejuvenation of cables. So what are our conclusions? Underground cables, they represent a critical high-risk asset class due to the many degradation factors that can result in cable failure, coupled with substantial financial and customer impacts of outages. Now, a risk-based asset planning approach, it's really a best-in-class approach for cable management because it lets utilities predict when failures are going to occur. We can quantify the impacts of failure, considering all of the different categories relevant to a utility. We can determine when is the optimal time to intervene, and this approach allows for different interventions to be considered. In the case of cables, we're really showing to regulators that we're considering all of our options. Do we want to replace? Do we want to rejuvenate the cables? And we're intervening when the costs, the risk costs and capital costs are all properly balanced against each other, or this economic end-of-life criteria. Now, data optimization and validation can, as part of continuous improvement, can help make failure probability and health index calculations more accurate. Results can be further enhanced over time by introducing additional parameters. This approach should take into consideration, again, the different alternatives, intervention options available to utilities, including replacement and injection. And by replacing or rejuvenating cables at their economic end of life, this is how utilities are able to minimize their total costs of ownership. So I wanted to thank everybody for listening to today's presentation, and I think we do have some time for questions.
All right, thank you, Robert. We have received some questions from our audience. The first one is, what kind of results do you usually get from this approach?
What we typically see with utilities, and this is because in most cases utilities have just transitioned into a proactive asset management approach after formally running a lot of their infrastructure to failure over many years. And so we'll typically see a backlog of equipment that needs to be intervened on immediately. And so what the utility needs to do next is basically develop a long-term program that aligns with their resource constraints, system constraints, essentially what they're able to execute operationally, and then they can determine when is that backlog going to be mitigated over time, or in essence, when are they going to achieve that economic steady state through the investments that they're performing.
All right, thank you. And our next question, Your health index includes maintenance and inspection data. What do you collect as inspection data for buried cables?
In terms of inspection data, so that's going to vary for different cable types. So depending on, like for instance, if you've got cables and chambers, there will be certain inspections that could be done on the splices, for instance. It really depends on what type of inspection work that utilities are performing. There's a lot of utilities that don't perform any inspection on their underground cables, but we are seeing some utilities that are performing certain inspections, especially for cables that would be installed in chambers. So they'll take a look at the splicing, and that information could potentially be used as part of a health index architecture.
All right, thank you. Our next question, do you have a recommendation on how a smaller utility with a limited budget and limited data could implement this plan?
Absolutely. So this is a type of implementation that is very scalable. Often the question I get is, does this require a lot of data and a lot of expense to getting the data? Usually the answer is no. In fact, usually we've surprised utilities with how much data they actually have, and it's really just a question of making sure the information is properly centralized. We work with utilities in performing that centralization. And then where data is legitimately unavailable, there's a lot of industry-based parameters that can be used. There's been a lot of global studies that have been done as well. So one example is, for instance, the customer interruption costs, which most utilities won't have their own customer interruption cost. But of course, there's been a number of North American, US and Canadian studies that have been done to establish these values. And in fact, there's tools out there that utilities can use. So they just plug in their safety value and they get a customer interruption cost that's relevant to their population. So there are a lot of industry definitions and information that can be available to fill in those gaps. And then it's important to have the processes continuously improve. So now the utilities know what they're looking for, and they continuously refine their processes over time such that they are able to localize those assumptions and localize the information as it relates to their utility, and ultimately make enhancements to their planning approach.
Great, thank you. One more question. How do you determine the probability of failure for a given cable?
So can you repeat that again? So the probability of failure for underground cables? So essentially, we'll determine that probability by looking at essentially the asset life data. So basically determining when were cables first installed in the system, when were cables ultimately removed, performing basically a series of data optimization, so censoring and filtering of that information to make sure that we're just looking at data that reflects assets that were removed due to end-of-life considerations or actually failed. And using that information, we can develop probability distribution functions that gets converted into what we call a survival rate function, and then finally that gets converted into a hazard rate distribution function. So it's really looking at the utilities' asset life information as it relates to underground cables. And then condition information can also be used to establish a relationship between, okay, how long is it taking essentially for a cable to degrade from very good all the way to very poor, and then converting that into a condition-based failure probability calculation.
All right. Thank you, Robert. We did have a couple of people ask if this presentation will be available later. And yes, we will have a recording up on novinium.com later today. Thank you so much, Robert, for taking the time to speak with us today. And thanks to everyone for joining us. Please take some time to complete the survey at the end, and we hope you enjoyed the webinar. And we look forward to our next Masters of Reliability webinar. Thank you.